Section: Introduction. In this section, we explore the outputs of o1-Like models when faced with challenging math problems. We begin by highlighting the frequent switching of thoughts observed in their responses, which significantly differs between correct and incorrect answers. This behavior often leads to a lack of depth in reasoning, as the models tend to abandon promising lines of thought too early. To assess this underthinking issue, we propose a metric and present our empirical findings. Our analysis shows that o1-Like LLMs frequently underthink, particularly when tackling difficult math problems. We conduct experiments using 3 test sets: Math 500, which includes high school math competition problems across various subjects and difficulty levels; GPQA, a graduate-level dataset with multiple-choice questions in science; and Amy, which tests problem-solving skills in different math areas. We focus on 2 well-known open-source o1-Like models, QWQ32B Preview and DeepSeek R1-671B, both of which demonstrate clear chains of thought. Additionally, we evaluate DeepSeek R1 Preview on the Math 500 and Amy sets, despite its daily message limit. Section Summary. In this section, we analyze the outputs of o1-Like models on challenging math problems, highlighting a frequent tendency to switch thoughts, which leads to inadequate depth of reasoning and premature abandonment of promising paths. We propose a novel metric to assess this underthinking phenomenon and demonstrate that it significantly impacts the model's performance on difficult tasks. Section: Definition of reasoning thoughts. In this section, we define thoughts as the cognitive steps we take while reasoning, generated by our model. o1-Like large language models, LLMs, often change their reasoning thoughts using phrases like alternatively. For example, in our problem-solving process, we move from algebraic manipulation to geometric interpretation and optimization strategies. This ability to switch between different reasoning strategies allows us to explore various solutions and shows the model's flexibility in addressing complex problems. We analyze the side effects of this thought-switching ability using the LLMs 3.3-70B model, which excels in following instructions and performing mathematical reasoning. Initially, we manually reviewed responses from the QWQ32B preview model to identify expressions that indicate shifts in thought. Then, we had the LLMs 3.3-70B model scan the entire response to find all such expressions and determine if they truly indicated a change in thought or were just stylistic. We only used expressions that genuinely signified a thought shift as separators in our reasoning processes. We found that o1-Like LLMs switch thoughts more frequently when faced with harder problems. Our analysis of the Math 500 test set shows that as problem difficulty increases, all models generate more reasoning thoughts, which aligns with the increase in generated tokens. This suggests that these models adapt their reasoning processes to tackle more challenging problems. When we looked at how o1-Like LLMs handle incorrect responses, we noticed a significant rise in thought switching across all test sets. This indicates that while the models adjust their cognitive processes to solve problems, more frequent thought switching does not necessarily improve accuracy. They may be using more computational resources without achieving better solutions. This highlights the importance of exploring cognitive pathways efficiently to enhance accuracy, even in complex reasoning tasks. We also considered the possibility of underthinking in these models. Frequent thought switching and incorrect responses could arise from either genuine underthinking, where the model finds good strategies but fails to follow through, or from a lack of understanding, leading it to explore ineffective approaches. To clarify this, we propose a framework to assess whether an abandoned reasoning path could have led to a correct answer. By examining if the model can consistently pursue a promising line of thought, we can identify instances of underthinking. In our assessment of thought correctness, we found that some early thoughts can lead to the right answer. For instance, one thought correctly identifies that the given equations resemble those of ellipses. However, instead of thoroughly exploring this thought, the model frequently shifts focus, using many additional tokens without reaching a correct conclusion. We use LLMs to evaluate whether each thought leads to a correct answer, employing two models distilled from DeepSeek R1 to 671B based on Llama and Qwen. If at least one model gives a confidence score of 2 for a thought, we consider it correct. We tested our assessment approach using responses from Qwen 32B preview across 90 instances from the AMI test sets. We compared the final thought in each response to its correctness. We ensured a fair comparison by matching the lengths of correct and incorrect thoughts. Our results showed an accuracy of 82.9% for correct thoughts and 81.8% for incorrect thoughts, demonstrating the effectiveness of our assessment method. Section Summary. In this section, we define reasoning thoughts as the cognitive steps taken by the model during problem solving, noting that o1-Like LLMs frequently switch these thoughts, especially when faced with more complex problems or incorrect responses. We analyze the implications of this thought-switching behavior, suggesting it may indicate underthinking or ineffective exploration, and propose a framework to assess the correctness of these thoughts, achieving high accuracy in distinguishing correct from incorrect reasoning paths. Section. Early-stage thoughts are correct but abandoned in incorrect responses. In this section, we discuss our findings on early-stage thoughts in incorrect responses. Our analysis reveals that many initial thoughts across different models are correct but are often abandoned too soon. This tendency to shift away from promising ideas suggests that the models lack sufficient depth in their reasoning, leading to potentially correct solutions being overlooked. We believe there is a need for models to better explore and develop their initial correct thoughts before moving on to other ideas. We also found that over 70% of incorrect responses contain at least one correct thought, and in more than half of these cases, over 10% of the thoughts are correct. This indicates that while some models can start on the right track, they struggle to follow through to the correct conclusion. Therefore, it is essential for models to maintain and build upon their initial correct thoughts to arrive at accurate answers. This leads us to propose a new metric for assessing underthinking based on the presence of the first correct thought. We introduce an underthinking metric that evaluates token efficiency alongside the traditional accuracy metric. If a model generates a correct thought early on but then shifts to other thoughts without reaching a correct answer, the subsequent tokens are deemed inefficient due to underthinking. We define the underthinking score as a measure of how effectively tokens contribute to generating correct thoughts. A lower score indicates higher efficiency, meaning more tokens are used effectively before switching thoughts, while a higher score reflects greater underthinking, with many tokens being irrelevant or redundant. Our empirical results show that all models we examined exhibit significant underthinking issues, though the extent varies across different models and test sets. For instance, the DeepSeek R1 to 671B model shows higher accuracy on some datasets but also higher underthinking scores, suggesting it may engage in longer but less effective reasoning. Conversely, on the AMI 2024 test set, this model achieves both higher accuracy and lower underthinking, indicating more efficient reasoning. These findings highlight that underthinking behavior is influenced by the specific dataset and tasks. Increased model capacity does not always lead to less underthinking. In some cases, it results in more complex but inefficient reasoning. Understanding underthinking is vital for developing models that not only provide correct answers but also demonstrate effective reasoning processes. Section Summary. In this section, we analyze the tendency of models to abandon correct initial thoughts in incorrect responses, revealing that over 70% of these responses contain at least one correct thought, indicating a need for models to better explore and develop their reasoning pathways. We propose an underthinking metric to assess token efficiency, highlighting that lower scores reflect more effective reasoning, while higher scores indicate inefficient thought processes that fail to contribute to correct conclusions. Section. Mitigating underthinking issues. In this section, we propose a simple method to address underthinking issues without needing to fine-tune any models. Our experiments with the QWQ32B preview model show that this method works well across all difficult test sets. We found that models like o1 tend to explore many solutions rather than deeply analyzing one, To improve this, we introduce a new decoding method that includes a thought-switching penalty, encouraging the model to thoroughly consider its current thoughts before moving on to new ones. In standard decoding, we calculate the likelihood of each token at a given position using a softmax function based on the model's output scores. This process is repeated for each position to generate sequences of tokens. To help the model focus on its current thoughts, we add a penalty for tokens that indicate a switch in thought. We define a set of tokens related to thought transitions and adjust their scores based on two parameters: the strength of the penalty and the duration for which it applies. A stronger penalty makes it less likely for these tokens to be chosen, while a longer duration encourages the model to stay on a thought longer. We conducted our experiments using the QWQ32B preview model since the DeepSeek R1-671B API does not allow score modifications. We varied the penalty strength and duration to see how they affect the model's performance. Our results show that increasing the penalty strength generally improves accuracy up to a point, after which it levels off or declines. Similarly, adjusting the penalty duration has a significant impact. For example, with a lower penalty strength, increasing the duration led to notable accuracy gains. We selected specific values for the penalty strength and duration for our further experiments. Our results across 3 challenging test sets demonstrate that our approach consistently enhances accuracy compared to the standard QWQ32B preview model. By penalizing thought switches, we encourage the model to elaborate on its reasoning more thoroughly, which aligns with effective human problem-solving strategies, especially in complex scenarios. Section Summary. In this section, we propose a lightweight mechanism to mitigate underthinking issues in language models without fine-tuning, demonstrating its effectiveness through experiments with the QWQ32B preview model. We introduce a thought-switching penalty during decoding to encourage deeper exploration of current thoughts, leading to improved accuracy across challenging test sets. Section: Related Work. In this section, we discuss related work on scaling test time compute and improving reasoning in models like OpenAI's o1. We note that enhancing test time compute typically involves 2 main strategies. The first strategy is to expand the search space, which means exploring a wider range of potential solutions during the decoding process to achieve better results. Techniques such as self-consistency, where multiple answers are generated and the most common one is chosen, fall into this category. Other methods include best-of-n decoding and minimum Bayes risk decoding. The second, more transformative strategy focuses on mimicking human-like deep thinking. Models like QWQ, DeepSeek R1, and KIMI 1.5, which aim to replicate o1, use reinforcement learning to develop advanced reasoning skills. Through extensive RL training, these models demonstrate human-like thinking, allowing them to consider various strategies, reflect on their choices, revisit earlier steps, and verify their conclusions. This capability significantly enhances their accuracy, particularly in complex reasoning tasks. We also address the efficiency of reasoning in o1-like models, which is crucial for tackling difficult problems. While human thought can sometimes be inefficient, models can face similar challenges. For example, some studies have shown that these models may waste computational resources by revisiting obvious paths. Our focus, however, is on the issue of underthinking, where a model fails to thoroughly explore promising paths and instead shifts strategies too quickly, leading to wasted computation. This is especially problematic for complex problems, contrasting with cases where too much effort is spent on simpler tasks with little benefit. We argue that intelligent systems should learn to allocate their computational resources wisely, focusing on challenging and promising paths. We also explore the role of penalty mechanisms in natural language processing decoding. Traditional methods like greedy search and beam search often prioritize maximizing the likelihood of generated sequences without considering the overall quality of the outputs. Researchers have pointed out the limitations of these methods, prompting the investigation of penalty mechanisms to improve text generation. Length normalization is a common strategy used to adjust penalties, helping to prevent models from producing overly long or short translations, thus enhancing fluency and adequacy. Coverage penalties have also been introduced to address issues like overtranslation and undertranslation by discouraging repeated attention to the same tokens. In our work, we adjust decoding penalties specifically to tackle the problem of underthinking. Our approach encourages models to stick to their original reasoning and engage in deeper thought processes, reducing the tendency to frequently change strategies and engage in superficial reasoning. To our knowledge, we are the first to examine how decoding penalties can effectively address the issue of underthinking.